Hello, my name is Jacob Pellicott. I'm an undergraduate research assistant here at the University of Texas at El Paso, and today I'll be going over the analysis of 4-point bend fixtures and adapters. Here's the outline in which I'll be covering today. Basic overview, so I'll just start with the motivation and background of the project, followed by the objectives. Following this, I'll then go into depth of the simulations that I've ran using ANSYS Mechanical. So let's start off with the motivation. So as of today, there's considerable amount of interest in airtight seals or hermetic seals used for high reliability commercial and military applications. As you can see, I've included two pictures here, two examples, one being a satellite and the other being geophysical equipment. So this just kind of shows the broad spectrum in which these seals can be applied for, anywhere from space to determining rock formations underground. So to meet this need, seals must be designed and tested to ensure resistance to the wide range of extreme temperatures and pressures that they'll be exhibited to. Overall, this will increase the effectiveness of regulating the flow of fluids. So mechanical testing equipment with environmental chambers allows us to test these seals at extreme temperatures and pressures for the characterization of these seals. Below I've included examples of glass ceramic hermetic seals and then pictures on how they're made. Along with this, I included a simple testing machine to just illustrate the type of equipment used throughout the engineering world to characterize these materials. So next I'll talk a little bit about the background information that leads us to our objectives. So we'll be characterizing the materials or properties of these hermetic seals. By doing so, we'll follow the ASTM standard C1161, which covers the determination of flexural strength. This standard explains thoroughly about the apparatuses used, specimen requirements, testing procedures, calculation reports. One important thing it discusses is the design of the 4-point bend fixtures that's shown below. This design is important as we'll be following the schematic when conducting our experimentation, just to ensure that there's nothing affecting the overall flexural strength. So now that we understand the testing method and standard that we'll be following, I'll go over the equipment that we'll be using. So for characterization of these materials, we'll be using an Instron 5969 series electromechanical testing machine with a 50 kilonewton load cell. To ensure extreme temperatures are reached, an ATS split tube furnace is that's capable of reaching temperatures of 1200 degrees Celsius. And for testing, adapters are utilized to connect the 4-point fixtures to the Instron 5969 test machine. So this leads us directly into our objectives. So hermetic seals are used in many cases to isolate different environments from one another. The fabrication of new seals requires 4-point bend tests to be performed to ensure that the material is able to withstand these elevated temperatures while maintaining a sealed environment. Currently, there's a lack of miniature adapters that are capable of being used in an ATS split tube furnace just due to the space constraints. So our research objectives of this project is to design and analyze a high temperature 4-point bend fixture that's suitable for the ASTM standard to evaluate how the design system combats against compressive and buckling failure during testing. So here's our geometry that we'll be using. The system is basically a rod connecting to the 50 kilonewton load cell, and then with this, the dimensions are then based on the ATS split tube furnace. From the rod, it connects to a round fixture at the bottom with supports for the 4-point configuration. And this is just an exploded view just to kind of show what this geometry entails and what we'll be simulating today. So here we have a rod drawing for our geometry. This is then followed by the support fixture drawing, the round fixture drawing, and the pin drawing. So next I'll kind of go into the boundary conditions that I've used. So static structural analysis was performed to determine the displacements and stresses on the structure. This analysis was chosen as there are no loads induced by inertia and dampening effects. A force of 50 kilonewtons was applied to the pinhole at the top of the adapter, and a fixed support is applied to each of the cylindrical barrels. For mesh optimization, This structure has three sweepable bodies, so the pin, cylindrical barrel 1, cylindrical barrel 2. Because of a mixture of sweepable and non-sweepable bodies, a multi-zone method was applied to divide the non-sweepable bodies into several bodies and then apply sweep to the entire structure. For this multi-zone, you can see that the mapped mesh type was hexa, the free mesh type was tetra, and the sweep element size was 1 meter. With this, I have an example on the right-hand side. As you can see, the sweepable bodies are lit up in a neon green, while the rest of the body is its constant color. So here we have the entire mesh. On the left-hand side is the entire geometry, while the right-hand side is a sectional view. With this mesh, we use an element size of 9e to the negative 3 meters. Adapting size was on. The resolution was 7. The span angle center was fine. And as you can see, our skewness is below. With this skewness, it does appear that we have a good quality mesh as our values are close to 0. However, the 0.87 is the only value that could give us issues within the mesh itself. With this, our nodes is about 30,000 and our elements are around 18,000. So the simulations that were selected in ANSYS Mechanical GUI for this project include the total deformation, which provides overall sum of directional displacements, the directional deformation, which displacement over a system in the x-axis, where I provided a local coordinate system for our geometry. I then do equivalent stresses, or the von Mises stress, and finally the maximum principal stress. So here we'll have the total deformation curves. On the left-hand side, we have the 22 degrees Celsius, and on the right-hand side, we have the 500 degrees Celsius. Between these two, you can see there's only about a 5.4% coefficient of variation between the two, and because the increase of temperature, you can see also an increase in the total deformation from one to the other. Similar to the total deformation, here we have the directional deformation. So again, there's about a 5.4% difference of coefficient of variance between the two. With this also does show that there is an increase with deformation as temperature increases in the specimen. Next, we have equivalent stress. With this equivalent stress, again, we have the 22 degrees Celsius on the left and 500 degrees Celsius on the right. With this, we have a 0.5% coefficient of variation with the maximum value and a 4.2% coefficient of variation with the minimum values. With this, you can also see again that due to the increase in temperature, we have an increase in our stress values within the material. Lastly, we have the maximum principal stresses within our geometry. Like I've said before, we have the 22 degrees Celsius on the left and 500 degrees Celsius on the right. With the maximum values, we have about a 0.6% coefficient of variation, and with the minimum values, we have about a 3.1% coefficient of variation. Finally, with our conclusion, so the objective again for this project was to design a high temperature 4-point bend fixture and evaluate how it combats against modes of failure. This is in green because at 22 degrees Celsius and 500 degrees Celsius, it was confirmed that the design system is capable of handling extreme temperatures and loads for experimentation. With these successful design testing is now able to begin on glass ceramic hermetic seals to characterize the material properties. The future work for this research is continue to run eigenvalue buckling, linear and nonlinear analysis on high temperature 4-point fixtures and adapters to ensure their safety. Due to the limitations set on ANSYS research and student, I would like to continue to revise the mesh for more accurate and consistent results, as many times of optimizing the mesh, I would get many errors with the software that I currently have. Lastly, is just continue to conduct simulations with design specimen to determine the theoretical modes of failure for these type of tests. Again, my name is Jacob Pellicott. I'm here at the University of Texas at El Paso, and I'm an undergraduate research assistant with the Materials at Exchange Research Group. Thank you for listening in. I hope you have a great day.